Hi everyone, and welcome to this example video where we're going to see how we can use the theory we saw in the previous video. Let's say you have a function and you want to calculate the inverse Laplace transformation of it. That means you want to evaluate the Bromwich integral. And if you recall that to evaluate the Bromwich integral, all we needed to do was to calculate the residue of e to the power st of this function f of s that is finite, that has finite amount of isolated singular points on the s plane and is analytic on the rest of the plane. That means it's analytic everywhere except for a finite number of isolated singularities. And there should be a sum. That's the thing we needed to do. So today we're going to see two examples. Let's say example 1. This is example 1, and our f of s is given by the following. It's 1 by s square plus a square. So this f of s is coming from some f of t. That means there was some f of t. Someone did a Laplace transformation of it like this, and this is the output that person got, right? And let's say now that person has given you this function and asked you that what was f of t. That's what we wanted to calculate throughout the Bromwich integral, right? And our theory said that f of t is just the residue of this whole thing, e to the power st times f of s, this whole thing's residue. So the first thing we need to do, we need to find a pole. That means the poles are over here. So the pole will come from by making the denominator 0, and this is just telling you s is equals to plus minus is. So if you draw the Bromwich contour, which is really not necessary, but just for visualization purpose, I'm drawing the Bromwich contour, and let's say this is I, this is minus I, and you want to close it like this, anti-clockwise, positively oriented contour. So this is just for visualization purpose. You can even do this whole thing without drawing anything if you know the theory properly. So now all we need to do, since there are two singular points, we just need to calculate the residue at these two singular points. The sum of the residues at these two singular points of e to the power s t f of s, right? So let's try to calculate them. So there are two singular points, there will be two residues, right? And these are simple poles. That means pole of order 1, because this guy can be written as 1 by s plus ia and s minus ia, right? So these are simple poles. So using the formula for the residue that you saw in your previous week, it's fairly easy to calculate them. So I'm just gonna write down the formula for the residue. So let me just remind you what was the formula for the residue. Let's say for some isolated singularity z0, this was written as limit z goes to z0. Obviously it has mth order pole, let's say, and this will look like 1 by m minus 1 factorial ddd of m minus 1. Okay, since we are using s, let's use s over here. Oh, sorry, we are using z. Sorry, this shouldn't be s, this should be z. And this was it, right? So this was the formula, and using this formula we are going to calculate the residue. So the first thing we're going to do, we're going to calculate the residue for the point ia. And this is fairly easy. It's just a simple order pole. So all we need to do is that we need to calculate the residue of this e to the power st f of s thing at s is equals to ia, right? So f of s was e to the power st. Yeah. So if you use this formula, okay, let me show you the whole thing. F of s was simply 1 upon s square plus a square. That means s plus ia and s minus ia. Since we are calculating the residue at a point IA, we need to get rid of s minus IA. So that's why you need to multiply this s minus IA just in analogy with this formula. So then this is s squared plus a squared thing, right? And you are using the limit, or you can obviously write it over here. So let's use the limit first. Limit s goes to IA, and this will be just e to the power st s plus IA, right? And then if you evaluate the limit, that means you have to put s is equals to IA, or you can directly put it on this line as well. I'm not gonna do that, just for more details. So now put s is equals to IA and you are done. This is one of the residues, right? Now similarly, if you calculate the residue for the other singular point, that means minus IA, in the denominator you will get a minus 2IA, and in the numerator you will get a minus IAT, something like this. That means this is minus 2IA e to the power negative IAT. Now two singular points, two residues, and we are done. We just need to sum them up. So summation over the residues is just, summation over the residue of e to the power st f of s, where f of s was 1 by s squared plus a squared, is simply e to the power IAT by 2IA minus e to the power negative IAT by 2IA. Now you can already see this is a function of f of t. At this point you are done, but we can do more. What we can do is that we can use the trigonometric identities to make the result in a more compact form. Show the result, sorry, not make the result. And these are kind of equivalent, but whatever. And this is just sine of AT, right? A sine AT. And that's it. If you write it in a more gentle manner, it will look something like this. So this was your f of t, and when you Laplace transformation this f of t, you will get 1 upon s squared plus a squared. Okay, very simple. Let's consider another example. This is example 2. It's fairly similar, but this time the calculation will be a bit of painful. This time our f of s is something like this: s squared plus a squared whole squared. Now you can write it as s plus ia whole square and s minus ia whole square, and these are poles of order 2, right? That means if you use the formula of the residue, there is one derivative there. That means what I'm talking about is this guy. When m is equals to 2, that means you have to take the first derivative. So we have to calculate again the residue of e to the power st f of s, right? And now we are going to have to put the value of this f of s, and we have to indicate at which point we want to calculate the residue. So let me again start with the point residue at IA. That's the point I'm interested in. Now let's write everything formally. S goes to IA, second order pole. That means 2 minus 1 factorial. That is just 1, but still I'm writing it formally, so that's why I'm not skipping any kind of steps or any logic or any kind of whatever. So this is the first derivative of e to the power st s plus ia whole square s minus ia whole square, and here there will be, since I'm calculating for point ia, there will be this guy, and these two will cancel each other out. There is no need to write that in fact, but since I'm doing it formally, that's why I've written it. So limit s goes to a, and finally you have to take the derivative of it. That means derivative of e to the power st by s plus ia whole square, right? So now it becomes pretty easy. Sorry, yeah, there should be 2 second braces. And now first you take the derivative, then you take the limit. Sorry, s should go to ia. and if you take the derivative, this will be limit s goes to ia. Let's use the product rule over here to save our lives. This will be t e to the power st by s plus ia whole square minus s plus ia whole cube 2 e to the power st, something like this. Now I can easily substitute the limit. That means if you evaluate the limit, you just have to substitute s is equals to ia. So let's do that. Something like this. Okay, and you can now simplify this thing a little bit more. Let's try to see what happens if you simplify. You can factor out e to the power iat, you can factor out this 2ia whole square thing, and then you'll have t minus 2 by 2ia. This two cancels out, and this minus over here can be replaced with the plus sign, provided you put a minus provided you put a I square over there, and this I and this I will cancel out. There will be one I over here. So ultimately you will have this iat 2ia whole squared t plus ia, something like this. Alright, and similarly, if you calculate the residue for the point minus ia, and I'm not gonna write that in detail because I've already done it over here, and instead of plus ia over here, you will have a minus ia, and the plus ia will be over here. So what do I mean by that? I mean this limit s goes to minus ia, this will be just dds of, I'm skipping some line over here, so keep that in mind, because it's not necessary to write them all the time if you know what you're doing. This is s minus ia whole square, right? Okay, then take limit s goes to negative ia. You will have t to the power st s minus ia whole square minus s minus ia whole cube, and there will be 2 e to the power st, and now you just have to substitute minus ia instead of s. So this will be t e to the power negative iat by minus 2 ia whole squared minus 2 e to the power negative iat, and you have this minus 2 ia whole cube, and just like before we can simplify it a little bit. So let's try to do that. Whole squared t minus, what do we have over here? We have a minus 2ia, right? And these two cancels out, and this minus cancels out, so it results in a plus something. So this will be iat, and if you you can keep it or you can evaluate it, it's your choice. I'm just gonna keep it over here, and then this will look like 1 by ia. Yeah, and you can, if you want to keep some similarity with the previous result, now you can just play around with these i's. For example, instead of plus, if you want to write a minus, you can write the next line as e to the power iat, sorry, there will be a minus sign, negative i2a whole square and t minus ia, something like this. So we are done calculating the residues. Let's call this equation a, that's one of the residues, and this is b. Now to find the function f of t, by our theory that we saw in the previous video, this is just sum over the residues of e to the power st f of s, right? And we just add the residues that we found in equation A and B. So this, and in the next line we're adding the results from A and B. If you do that, let me just go back to see what was the result. Yeah, so this was e to the power iat divided by 2ia whole squared t plus I by a, and then plus, since this is a summation of the residues, the second residue was something like this, e to the power negative iat divided by minus 2ia whole squared times t minus ia, right? And that's it. You can now further simplify these things, or if you want, if you don't want, that's fine as well. But the idea is just to calculate the Bromwich integral that inevitably gives you the inverse Laplace transformation. So the summary is kind of like this. So if you have f of t something like this, you apply the Laplace operator, it takes you to the f of s thing, and this is the Laplace transformation. And the inverse Laplace transformation works through the Bromwich integral that gives you L inverse 1 f of s. It just spits out this f of t. It is done through the Bromwich integral. And this is how you can easily find inverse Laplace transformation for a given function f of s that is given to you, that is analytic through the whole entire S-plane except for a finite number of isolated singularities. And this is helpful because when you try to solve a differential equation, you can take a Laplace transformation of it, and that becomes an algebraic equation. And after you are done solving the algebraic equation, you need to use the inverse Laplace transformation to get the original solution of that differential equation. That's one of the many applications of this Laplace transformation. So this will be it for today, and perhaps this is the last lecture on your Math 215. So thank you.